Hello, chemistry students. Dr. Tullis here, finishing up chapter 13, looking at the importance of colloids. Colloidal dispersions, also called colloids, represent a state that's intermediate between a solution and a suspension. Colloids include many of the foods you eat and the materials around you, like jello, milk, starch, glue, fog, and porcelain, where particles are suspended but not dissolved. We have a dispersed phase where particles are distributed uniformly through a dispersing medium. Graham coined the term colloid from the Greek meaning glue to describe this class of substances that are distinctly different from true solutions and suspensions. The Tyndall effect is when we're able to scatter light and therefore materials often appear cloudy. Like we said earlier, colloids are classified according to the state of the dispersed phase and the dispersing medium. For example, aerosol is when I have a liquid dissolved in a gas, like fogs, clouds, aerosol sprays. We can also have solids dispersed in gases to give us smoke, airborne viruses, automobile exhaust. We can have gases in liquids, giving us shaving cream and whipped cream. We can have gases in solids to give us styrofoam and marshmallow. Liquid in a liquid, mayonnaise, milk, and face cream. Liquid in solids to be called a gel, to make jelly, jello, cheese, butter. Solid in a liquid, gold in water, milk of magnesia, and mud. We can also have solid in a solid called Sol. Milk glass is an example. I want to watch a few minutes of this video from Tyler DeWitt talking about colloids.
Let's talk about colloids. We'll look at some key properties and common examples. A colloid is a type of mixture that falls somewhere between a homogeneous mixture and a heterogeneous mixture. So, first off, a touch of review on types of mixtures. Here's a homogeneous mixture. This is more commonly called a solution. An example is sugar dissolved in water. In a solution, the dissolved particles are very tiny. They might be atoms, ions, or small molecules. And they spread out evenly, giving solutions a uniform appearance. A solution looks like one substance, and it doesn't separate out or settle out over time. On the other hand, in a heterogeneous mixture, the parts don't dissolve. Here is sand in water. You can see the distinct parts here. Now, if you stir things up, the different substances may hang in the water for a moment. They make what's called a suspension. But the parts always settle back out again. And the particles here are relatively big. You can see them. So, a colloid falls somewhere between a solution and a heterogeneous suspension. We'll use an example to make this clearer. We'll look at water in the air. Air is a homogeneous mixture of gases. There's mostly nitrogen and oxygen, but there's pretty much always some water molecules mixed in too. Molecules are too tiny to see, but we can zoom in. Here's a water. Because air is a homogeneous mixture, the parts don't settle. These molecules kind of float around, bumping into each other, but they never settle out. Now sometimes we get so much water in the air that it makes raindrops. And they're so large that they do settle out. The air can't support them, so gravity pulls them down. This is like how other heterogeneous mixtures settle out over time. But there's also an in-between. Sometimes there's just enough water in the air that tiny droplets form. Although these droplets are bigger than molecules, they're too small to settle. They just kind of float there. But they're big enough to start reflecting light, just like this. So you can see this. When this happens, you get something called fog. And fog is a colloid. It's made of very tiny drops of water dispersed or spread out in the air. So that's what we mean when we say that colloids fall between homogeneous mixtures and heterogeneous mixtures. The particles have a size that is in between or intermediate. Like a homogeneous mixture, fog stays suspended. It doesn't settle out. But like a heterogeneous mixture, the particles are visible. You can see them. So, let's talk about the parts of a colloid. Colloids always have two main parts. We call these parts phases. In fog, the tiny droplets of water are one phase, and the air is another phase. There are technical terms for these two phases: the dispersed substance and the dispersion medium. In fog, the water droplets are the dispersed substance, and the air is the dispersion medium. The dispersed substance spreads out and kind of floats in the dispersion medium. Now, there are different types of colloids. These depend on what the dispersion medium is and what the dispersed substance is. When you have liquid dispersed in a gas, like fog, you have a type of colloid called an aerosol. You might have heard that word before, maybe with like an aerosol spray can. Same as fog. Liquid is a dispersed substance, and air is the dispersion medium. Another type of colloid is smoke. Like fog, the dispersion medium is air. But with smoke, the dispersed substance is a solid, tiny pieces of burnt wood or rubber or paper. This type of colloid is also called an aerosol, solid, dispersed in gas. We can build kind of a table here.
Now this video continues, and I welcome you to continue watching it, but we are going to cover it as well. Tyler was just going over the different types of colloids, looking at the dispersed phase and the dispersing medium. So we have our aerosols, our foam, our emulsion, our gel, sol, and our solid sol. And we're going to go back to our notes. We now know that it's possible to crystallize some colloidal substances, albeit with difficulty, so there really is no sharp dividing line between these classes based on that property. Colloids do, however, have several distinguishing characteristics. Many of the substances that form colloids have high molar masses. This is true of proteins like hemoglobin that have molar masses in the thousands. The particles of a colloid are relatively large, several hundred nanometers in diameter. And as a consequence, they exhibit the Tyndall effect, which means that they scatter visible light when dispersed in a solvent, making that mixture appear cloudy. And even though colloidal particles are large, they are not so large that they settle out. Here's a little note down here looking at the picture. Graham also gave us those words sol for a colloidal dispersion of a solid substance in a fluid medium, and gel for colloidal dispersion that has a structure that prevents it from being mobile. Jello is a sol, a solid that is first mixed with boiling water, but it becomes a gel when cooled. Some other examples of gel are the precipitates, aluminum hydroxide, iron hydroxide, and copper hydroxide right here. Here are a couple more colloids that exhibit the Tyndall effect, and we can see them scattering light. Colloids with water as the dispersing medium can be classified as hydrophilic, which means water-fearing, or hydrophilic, which means water-loving. A hydrophobic colloid is one in which only weak attractive forces exist between the water and the surfaces of the colloid particles. We can see here in this picture, we have 3 hydrophobic colloid particles at the center, and they're surrounded by a single layer of positive ions and then sheathed by a multi-layer of negative ions, and negatives repel each other. So we have this repulsive force showed by those double red arrows. Soil particles are often carried by water in rivers and streams as hydrophobic colloids. When river water carries large amounts of colloidal particles, meets seawater with its high concentration of salts, the particles coagulate to form the silt that's seen at the mouth of a river. Hydrophilic colloids, on the other hand, are strongly attracted to water molecules. These groups are OH groups and our NH2 groups that are on their surfaces form strong hydrogen bonds to water, so it stabilizes the colloid. Proteins and starch are important examples of hydrophilic colloids, and homogenized milk is the most familiar example. Emulsions are colloidal dispersions of one liquid in another, like oil or fat in water. Familiar examples include salad dressing, mayonnaise, and milk. Now, if vegetable oil and vinegar are mixed together to make a salad dressing, the mixture quickly separates into two layers because we have nonpolar oil that do not want to interact with the polar water and acetic acid. So why are milk and mayonnaise apparently homogeneous mixtures that do not separate into layers? Well, the answer is because they contain an emulsifying agent like soap or a protein. An ingredient that's found in egg yolks, lecithin, can act as an emulsifying agent. So mixing egg yolks with oil and vinegar stabilizes that colloidal dispersion known as mayonnaise. Some other emulsifying agents here are soaps and detergents. Soap is made by heating a fat with sodium or potassium hydroxide, which produces anions and long chains of carboxylic acids, sometimes referred to as fatty acids. An example is sodium stearate. Shown here, this fatty acid anion has a split personality. It has a nonpolar hydrophobic tail that is soluble in other similar hydrocarbons and a polar hydrophilic head that is soluble in water. Now, if you were to get some oil on your clothes, let's say this is our fabric and you get some oil on it, oil can't be readily washed away from dishes or clothing. Think of the dishes you put in your sink if they have gunk on them, oil from your food. We need soap to help us with that. It's not going to just go away with water because oil is nonpolar and is insoluble in water. So we add soap to the water to clean that oil away. The nonpolar molecules of the oil interact with the nonpolar hydrocarbon tails of the soap, leaving the polar heads of the soap to interact with the surrounding water molecules. The oil and water then can mix and the oil can be washed away. We see here that our detergent has a polar head which likes water, a nonpolar hydrophobic tail that does not like water, but the nonpolar tail likes the detergent. So we can see the tail attacking the detergent and the head of it liking the water, and then it's able to just wash it away. An emulsifier, also known as an emulgent, is a substance that stabilizes an emulsion by increasing its kinetic stability. Then we have substances like the soaps we were just talking about that affect the properties of surfaces and therefore affect the interaction between two phases. They are also called surface active agents, or surfactants for short. A surfactant used for cleaning is called a detergent, like we just showed. One function of a surfactant is to lower the surface tension of water, which enhances the cleaning action of the detergent. Notice here, we have sulfur that's carefully placed on the surface of water. There is surface tension on the water that keeps the denser sulfur afloat. But if you add several drops of detergent on the surface of the water, the surface tension of the water is reduced, and then that sulfur sinks to the bottom of the beaker. I highly encourage you to read the Applying Chemical Principles that's at the end of the chapter in our books because it's really interesting. And then I have 13 join-in questions to wrap up this chapter. Again, I highly recommend you open up the PowerPoint and go through them because each one I give the answer to. That wraps up Chapter 13.